This is the video mark scheme for A2 Chemistry Paper 5 Energy, Equilibrium, Energetics and Elements for June 2013. Right, so I've written out the definition. For the first question, there's 2 marks available. The important parts of this are that it's 1 mole being formed and that it's formed from gaseous ions. So this is different from enthalpy change of formation, where it's formed from its elements. So for this one, you need to make sure you're comfortable with your ionization energies and electron affinity. So looking up from step D, we have calcium changing to calcium plus. And then step E, something is changing, that means that we end up with calcium 2 plus and oxygen minus. So the obvious thing here is that our second electron is being removed. Don't forget your state symbols. To form calcium 2 plus. Step F is then the first electron affinity of oxygen. So oxygen is going from an atom to a -1 ion. The next step is for that to become a 2- ion. Okay, now I don't include the electron there because the electron has been taken in by the oxygen here. Almost forgot on this side. Calcium has lost 1 electron, but there's 1 electron already, so that gives you 2 electrons overall. So over the page, the next question's asking you for the enthalpy changes for A, C and G. So let's start with A. And we are going from calcium solid and oxygen gas to calcium oxide. These are the elements in their standard states, and we're forming 1 mole of a compound. So this is going to be the enthalpy change of formation of calcium oxide. It needs to be in words, so on the next page I'll write them out in full. C is what is changing is our calcium is changing from a solid to a gas. So that is the enthalpy change of atomization of calcium. And G over here, oxygen is gaining a second electron. So that is the electron affinity, second electron affinity even, of oxygen. I'm going to write these out in full on the next page when I've got space to do that. So here are the 3 definitions written out in words. You can't use the symbols. The important part for this one is that it's formation and not lattice enthalpy. The second one, atomization and oxygen. So it's clear you didn't confuse it with the atomization of calcium. And for this one, the important part is that it's the second electron affinity. Okay, right, so using the Born-Haber cycle from the previous page, so calculating the lattice enthalpy, it's rather hard to show this without the chart in front of us, but ultimately This is the mark scheme. So this is the calculation with the final answer in there. If you get this number minus 3454, then you get 2 marks. There's a number of ones that you will get 1 mark for. So I'm just going to list the ones that you would get 1 mark for. So minus 3736, what's happened here is instead of minus 144, you use plus 144. If you get all of the signs wrong, then you get the same answer, but the sign's been reversed, so only 1 mark for that. If you get 2184, then you have put the wrong sign before all of this, so you'll have a plus there instead of a minus. Or you have the wrong number, the wrong sign before there. That'll still give you that will give you minus 2184 instead. And if you have minus 1858, you went wrong because you had the wrong sign for this. Okay. Right. If you made a transcription error where you perhaps got one of these numbers wrong because you copied it over incorrectly, so let's say you had 253 instead of 235, then you lose 1 mark. Okay, this question is essentially asking you about what affects the strength of ionic bonding. So we did this all the way back in Unit 1, really, and the 2 factors that we need to be thinking about are ionic size. So the smaller the ion, the more negative or more exothermic or more attraction between the ions. Notice that at no point do we say that that lattice enthalpy is bigger. Yep. Because it's a negative number, you've got to be really careful with that. Okay, and the second factor is increase ionic charge or increased charge density. That will give all of the same as we've got up here. The more negative the lattice enthalpy, the more exothermic or the more attraction between the ions. Okay, so that will give you the first 2 marks, and then for the final mark you've got to link lattice enthalpy with greater attraction. So the greater the lattice enthalpy, the greater the attraction between ions. Okay, so you get 1 mark for each part of this. 1 one mark for this part, one mark for this part, and one mark for this part. This part also needs to be linked to this bit here. So this is what's meant by half-life. You can get away without including this part here, its original value, and you don't need to say that it's concentration of the reactant, but you will lose the mark if you say it's concentration of product. Okay, so we only get this mark if you either don't mention it or you won't mention product. Okay. So you need to show on the graph 2 half-lives. I'm going to go for you guys will have to use a ruler. It's a little difficult to do this on the tablet. So the drop between 4 and 2 is going to be from 24 to 80. And then the drop from 2 to 1. Let's try that again. There we go. Could be 100. Ooh. Just realised I've read this one wrong, haven't I? Sorry, that is 28, not 24. And here is 134 minus 80. Right, so I've come up with 52 and 54. Half-life should be stated as 54. But provided you get anywhere between 50 and 56 seconds, that's correct. They'll allow it shown on the graph, but make sure it's nice and clear. Be careful because the initial concentration isn't 6, so you can't go from 6 to 3. So it's first order because the half-life is constant. Okay, I'm staying on this page even though we've gone over the page for the questions. If we started with twice the initial concentration, then the half-life would still be the same. It would still take exactly the same amount of time for it to drop by half. The reason I'm staying on this page though is for the next question, which is show the rate of reaction after 40 seconds. So this will involve using a ruler. I'm not able to do that on here, but you guys should have a ruler, and 40 seconds is here, so you need to draw a line. Easier said than done. A line and a tangent to the curve. Okay, you then calculate the gradient of that line. Hopefully you guys do a slightly better job than me, provided you get, let me just have a little look. Doesn't give me an error for how far away from the actual value it should be. My line is a bit off because I should end up about here instead. The final value No, can't see. So the EG that they've given me is 4.5 times 10 to the minus 2. But it will be based on your graph. It's got to be two significant figures, but they will allow you, very nice of them, to get the mark if you've done 0.04 rather than 0.040. But you guys should get into the habit of doing that anyway. Provided your tangent is reasonable, it looks like you get the marks regardless of the value, but I would expect it to be somewhere around 4.5 times 10 to the minus 2. So having calculated your rate here, the units, it's concentration over second, so your units are going to be mole per dm cubed per second. Okay, and then you get a separate mark for this. So 2 marks for drawing a tangent and calculating it. So 1 mark for the tangent, 1 mark for the calculation, and then 1 mark for the units. To calculate the rate constant, you need to take your answer from here. So your answer from here and divide by the concentration at that time. So you've got to go back to the graph, read the concentration at the point at 40 seconds, which was 3.45, and that will give you a value for K of 0.013. This one, they will allow you to use anything between 3.4 and 3.5. The units are going to be seconds to the minus 1, because this is in dm cubed per second and this is in dm cubed, so we're just left with seconds overall. If we use that, we get 0.013. However, you get the mark provided you've done this calculation correctly. Right, the order of this reaction with respect to water is effectively 0, and explain why. It's a slightly tricky question, but effectively water's going to be in huge excess because it's dissolved in water. That's the main reason, or you could say that the concentration of water is very large, or it doesn't change. So relative to the amount of reactants, the number of moles of water being added or lost through the reaction is very, very small. Okay, right, so we've got an equilibrium question here. I'm going to write out my equilibrium again. Okay, right, so we've got our start and our equilibrium. So at the start we had 2 times 10 to the minus 3 moles of hydrogen, 4 times 10 to the minus 3 of iodine, and none of this. At equilibrium we have 3 times 10 to the minus 4. So just to make it easier to see, I'm going to change that to times 10 to the minus 3, so it's easier to compare. That means that the amount of hydrogens that reacted must be 1.7 times 10 to the minus 3 moles. Okay. For every 1 mole of hydrogen that reacts, 1 mole of iodine will react. So to work out the number of moles of iodine, we're going to take our initial number of moles and take away the 1.7 times 10 to the minus 3. So that gives me 2.3 times 10 to the minus 3. Now, for every 1 mole of this that reacts, 2 moles of this are made. So it's going to be twice 1.7 times 10 to the minus 3, which gives us 3.4 times 10 to the minus 3. Okay, right, so there's a number of marks available for this. I'm just going to pop that in red. You get 1 mark for working out the number of moles of iodine, 1 mark for working out the moles of hydrogen iodide. We then going to go to our expression for Kc, which is going to be products squared over reactants. Sure, it's all times, so you don't have any pluses in there. And then we just put in the numbers. Which should give you overall 16.8. 3 significant figures are required. Okay, it's part of the question. Up here, 3 significant figures. So 16.8, and it's also asked for the units. What you should see is that we have moles per decimeter cubed squared on the top, and then moles per decimeter cubed squared on the bottom. So no units overall. If there are no units, make sure you write it or you don't get a mark for it. So 4 marks for this correct 3 significant figures, and 1 mark for no units. Okay, so if we have a look at the equilibrium here, we'll be changing the concentration of the hydrogen iodide, but not Kc. Kc only changes with temperature. So what we're doing is we will be increasing the concentration of hydrogen. So this goes up. The equilibrium overall will move in this direction in order to reduce it. So for Kc to stay as it is, this will need to get smaller, and so will this. Sorry, this will need to get bigger, and this will get smaller. So when the equilibrium moves in this direction, hydrogen iodide will get greater, the iodine will get lower, and the hydrogen will be higher than the first time, even though some of it is removed, not all of the extra hydrogen is removed. So 2 marks for getting all of that correct. And if you get 2 of the columns correct, so if you get 2 out of 3 correct, then you get 1 mark. Right, so the chemist heats the mixture to a higher temperature. Would Kc be greater or smaller or the same? In order to do this, you're going to go look at the beginning, and it tells you right at the beginning of this question that the enthalpy change is -9 kilojoules per mole. So this means that the forwards reaction is exothermic. If we heat it, we are going to be moving it in the backwards, so the equilibrium will shift to the left. That means that if we look at our equilibrium constant, if we move to the left, this has got smaller, this has got bigger, so overall Kc is smaller. If we increase the pressure, Kc is going to be the same as Kc is not changed by pressure. So it's only affected by temperature or not affected by pressure. Those are the two ways you can explain this. Okay, so we've got two acids here. We've got hydrochloric acid and chloric 1 acid. They've not given us the pKa for both. We've just given it for chloric 1 acid. But hopefully you should be able to remember that hydrochloric acid is a strong acid. And so you also need to state that is a weak, missed off the O, is a weak acid. So the chloric 1 acid is a weak acid. So 1 mark for that. Working out the P for HCl, to work out the pH, it's going to be minus log the concentration of hydrogen ions. I realise I've missed off an O in log, there we go, which equals minus log 0.14 in this case, as it's only 1 hydrogen ion per molecule of HCl, which gives us 0.85. Remember, it's got to be 2 decimal places. Okay, now looking at the weak acid. We're not given Ka, we're given pKa. So Ka is going to equal 10 to the minus pKa, which gives us 3.7 times 10 to the minus 8. Okay, 1 mark for this. Right, so Ka times 10 to the minus 8, Ka equals H over HA. In this case, for every hydrogen that's released, 1 anion is released, so H plus equals A minus. So I can rewrite this as H squared over HA. It's a weak acid, so we can count the concentration as being the same as the initial concentration up here. So that gives us H plus squared equals 3.7 times 10 to the minus 8 times the initial concentration, 0.14, and then to get our concentration of hydrogen ions we need to square root. That will give you concentration of hydrogen ions this is 1 mark here. Then when you do minus log concentration of hydrogen ions, you should end up with 4.14. If you forget to square root, then you get 8.28. You'll only get 1 mark from that instead of a mark from here as well. So we have 1 mark here, 1 mark down here, 1 mark here, 1 mark from the differences, and 1 mark for the pH for the strong acid. Total of 5. Okay, right. Next question. Want the full equation and the ionic equation. If it's reacting with aluminium powder, we're going to be making a salt. Metal plus acid makes salt. So full equation, aluminium will react with the acid. You guys will write it out first before you're balancing it. But you should remember that aluminium is a 3+ ion. So that means that you will end up with a total of 3 anions per aluminium. And we make hydrogen as our byproduct. In order to get it to balance, you need 2 of these and 3 of these. All on one line, but I can't fit that on. The ionic equation if we look at what's in solution, this and this are my 2 ionic compounds in solution, and so if I write out the full equation, the things that appear on both sides that can be cancelled off are the carboxylate ions, leaving us with the ionic equation. You're allowed to use fractions or multiples and you still get the mark. Okay, so we're calculating the pH of a sodium hydroxide solution. There's 2 ways of doing it. We can start off with Kw equals H plus OH minus. Now it's not a neutral solution, so H plus doesn't equal OH minus, as it does with pure water. Instead, we've added extra hydroxide ions. So Kw equals 10 to the minus 14. If I rearrange this, that gives me the concentration of hydrogen ions equals Kw over OH minus. Sodium hydroxide, it's a strong base, so we have 1 mole of hydroxide ions for each mole of sodium hydroxide. So that gives us Kw over concentration of hydrogen ions, which gives us 2.5 times 10 to the minus 14. That's our concentration of hydrogen ions, so pH is minus log concentration of hydrogen ions. which is minus log. Which should give you 13.6. The alternative way of doing it is that you use POH, so 14 equals pH plus POH, and POH in this case would equal minus log 0.4. Either method will give you the correct answer. Okay. Okay, we've got a 7 marks buffer question, and this one is based on methanoic acid. Okay, all too often, unfortunately, people are using H plus and A minus rather than the actual chemicals involved. So, first mark for these types of questions is basically a definition of a buffer. So a buffer minimises pH changes on the addition of small amounts of acid or alkali. In the mark scheme, small is in bold, so that means you do need to include it. It's important that it's clear it's only small amounts of acid or base. Right, our next mark is for doing the equilibria. So this is for methanoic acid. You've got to have an equilibrium sign. The whole point of how this works is because it's an equilibrium. So for the next 2 marks, you need to say that either H plus ions react with the added base. So instead of H minus, you can say alkali or base. So this is 1 mark for this, and then you get 1 mark for saying that the equilibrium will move right. Which would form hydrogen ions. So 2 marks for explaining what happens when you add a base. The next 2 marks are for what happens when you add an acid. So on adding an acid or H plus, the equilibrium is going to move to the left, forming more of the methanoic acid. Okay, again, there's 2 marks here. You get 1 mark for explaining what reacts with the acid, and 1 mark for saying which way the equilibrium moves. So far we've got 1 mark up here, 1 mark for the equilibria, the remaining 2 marks are quality of written communication. So if you're looking at the mark scheme, QWC stands for quality of written communication. That's a little bit hard for me to show on this mark scheme here, so I'll be taking them and having a little look at those ones. Right, so now we're looking at the buffer solution. And this buffer's been made by reacting a weak acid and a strong base. So our first step is to explain why a buffer solution is formed when these 2 solutions are mixed together. We then calculate the pH, and we've got to give our answers to 2 decimal places. When you finish a question like this, you should go back to the beginning and just check that you've done each step of what it's asking for. So have you explained this one? Have you explained this one? Have you done it to 2 decimal places? That's a really good habit to get into. It won't take you very long, but might save you losing silly marks for things like this. Okay. Right, so step 1, explaining why the buffer solution is formed. I'm going to write out the equation. So our weak acid will react with sodium hydroxide to make a salt. Salt, here we go. And water. Okay, there's 1 mark for doing this equation. You can also write that in words, but you should be using the formula. It's generally easier. So that's the first part. The next part is not all of the weak acid has reacted. So, or you could say that the weak acid is an excess. So this is our buffer of weak acid, and its salt is what forms a buffer, but you get the mark for making it clear that the weak acid was in excess. So we have 1 mark here and 1 mark here. Okay, so next step is asking us to calculate the pH. So what we need to do is work out the number of moles that we have after it's reacted. So we started off with 3. If I look at my acid first, we have a concentration of 3.2 and a volume of 0.2 decimeters cubed. So that's just 200 divided by 1,000 to give it to me in centimeters cubed. This gives me 0.64. So this is at the beginning before any of it's reacted. We added, so that's our number of moles at the start. We added 0.5 times 0.8 moles, so that's from this bit up here, to give us 0.4 moles of base. So after the reaction, after they've been mixed, so this is before, afterwards we're going to have 0.64 minus 0.4, giving me 0.24 moles of acid. And because for every mole of base, going by this equation up here, for every mole of base we formed 1 mole of salt. We have 0.4 moles of our salt at the end. Okay, right, I've moved it all up so I can have a little bit of space to do my workings out. So if I go from the basic equation here, missed off an H. Okay, I can use this to work out my pH. Okay, so from the question at the beginning, we have that Ka equals 1.7 times 10 to the minus 4. We're trying to find out our concentration of hydrogen ions. Our concentration of the methanoate ion will equal 0.4 divided by the volume, which I'm not going to bother to calculate. The reason will become clear. And our concentration of our acid is equal to 0.24 divided by volume. This means that I can cancel off the volumes, giving me an equation which, if you rearrange, you will get that the concentration of hydrogen ions equals 1.7 times 10 to the minus 4 times 0.24 over 0.4. You can then use pH equals minus log hydrogen ions to get your final answer, which in this case equals 3.99. I'm just going to draw your attention to this bit here. Give your answer to 2 decimal places. So if you haven't done that, you lose a mark. If you've got the right final answer, that's 4 marks even without showing your calculation. There is an alternative. You can also use the Henderson-Hasselbalch equation, which would give you pH equals pKa plus log base or salt over acid. So that will also give you the same answer. Okay, this question isn't in the mock that I gave my group in 2016, but we might be going through this later, so I'm going to include it in this mark scheme. This is a transition metal question. We're talking about complex ions here, and there's quite a lot of information. So first question is asking us to write an equation for the formation of solid A. So up here, whatever solid A is, it dissolves in water to form an orange-brown solution that contains this this complex ion. Solid A is formed by heating iron with chlorine. So we know that we're going to have iron, and we know we've got chlorine. For the oxidation state of our iron, if we come and look at the complex ion it forms, we can see that it's 3+. So if iron is 3+, chloride ions are -1 each. We're going to need 3 of them. To get this to balance, you need 2 ions, 3 chlorides, and 2 of these. Okay. You will get the mark if you put your product as Fe2Cl6, which is a reasonable deduction. You're also, if you have multiples, and you're going to, so if you have multiples or fractions of this, you also get the mark. Okay, our next one here, we're going to add aqueous sodium hydroxide, and we want to know what the precipitate is. We know we have iron 3 ions from the previous question, so it's an ionic equation. When it's precipitation, you can just do the 2 ions that react together, going to make the solid. If you want, you can go through with the spectator ions, but this is quicker. If you're making a precipitate, you know that you have 2 aqueous ions that come together to form a precipitate. Right, so the next one looks a bit confusing. Not one you're necessarily expected just to know off the top of your head, but you should be able to deduce what's happening. The clue here is that you have a pale green solution, which you should know means you have iron 2 ions present. So going through, we start with zinc powder, and we know our solution X is complex iron. On the other side, we've made a new complex, and it's pale green, so that means the oxidation state of our iron has changed from +3 to +2. That means that our iron has been reduced, which means our zinc has been oxidized. Now, to get this to balance, we're going to, each zinc has gained 2 electrons, so we need twice as many iron complexes, which will each give 1 electron. So this type of reaction that we have going on is redox. Our zinc was oxidized and our iron was reduced. Okay, so for experiment 3, we need to write an equation for the formation of the complex iron. Unfortunately, questions on the previous page, but if you read through, what we are doing is we are adding K potassium cyanide, which goes yellow. The fact it goes yellow tells you a reaction has taken place, and we are forming E, and E has a molar mass of 211.8. Okay, now what is happening is the ligands, which in X are water, are being replaced by the cyanide ions, and you can quickly check because iron is, I think, 55.8. I haven't got a periodic table in front of me, but that looks about right. And each cyanide ion has a mass of 26. That's 12 plus 14. 211 minus 55.8 gives you the mass of the cyanide ions. We'll just grab a calculator. Which gives us 156. If we divide that by 26, that gives us 6. So we know we have 6 cyanide ions present. Right, so X is our iron complex. All 6 ligands are going to be replaced with a cyanide ion. Now, because each cyanide ion has a negative charge, we have a +3 ion, but 6 negative. Let me just take off that negative sign. That's 6 negative cyanide ions. That gives us a total charge of 3 minus. Sorry, I'm running out of space a little bit, and 6 water molecules left over. If you get it all correct, then that's 2 marks. You get 1 mark for the correct product here and 1 mark for the equation. This type of reaction is called ligand exchange. Okay, in experiment 4, we form 2 optical isomers. So the optical isomers are the ones that are mirror images of each other. You get a mark for either way of writing this. So let's do one. Remember, when you're drawing these, it's best off to start with your iron in the middle first and draw the 6 coordinate bonds. So I start in the middle like this and then work outwards from there. Each one will bond to 2 oxygens. Oh, I've made that double bond and it shouldn't be. There we go. So this is a bidentate ligand. Running out of space at the bottom here. There we go. Move it all up a little bit. Okay. So this is the best way of drawing it. Start from the middle, work your way out. And the whole thing has a 3- charge. So this is one of our optical isomers. The other one should be a mirror image. So I start off in exactly the same way. Start from the middle and work out, but this time I'm making sure that it's a mirror image of this. Obviously you can be a little bit neater. This isn't the easiest medium to draw in. Okay, so the charge needs to be on the outside brackets in both isomers and no charges on the inside, so I also need to include the charge here. 1 mark for each isomer. And what's the third mark for? So, and the third one, if you've got your -3 charge on the outside of the brackets of both isomers and no charges shown in the middle for the third mark. Okay, right, so we've been asked to work out the standard entropy of glucose. So this is using a calculation we've come before, but just in a slightly different way. Hopefully you can remember that the enthalpy change of a reaction is equal to the sum of the entropy of the products minus the sum of the entropies of the reactants. Okay, so I'm going to put in the numbers of the ones that we do know. We know that the enthalpy change is -256. The enthalpy of the products is 6 oxygens and 1 glucose, which is the one we don't know. So I'm going to call that SG for glucose. And we're going to be deducting 6 CO2 and 6, the entropy of 6 waters. Okay. If you work that through, you should end up with 218 kilojoules per mole. If your answer is 218, you get 2 marks regardless of how you've shown your working out. If you have -218, then you just get 1 mark. So 1 mark for having the wrong sign and 1 mark for 730, which is where you've done, I'm not sure what you've done there. Okay, if you've added them together, which is -3190, you don't get any marks. Okay, right, so you're now being asked to calculate Gibbs free energy. which is this. Now, common mistake here is to forget that our entropy is in joules per Kelvin per mole, and our Gibbs is in kilojoules per Kelvin per mole. So when we're putting in our numbers, we've got the entropy, which is earlier on in the question, minus, and this is standard conditions, so our temperature is 298, but our entropy is divided by 1,000 to convert it from joules per Kelvin per mole to kilojoules per Kelvin per mole. Overall, this would give you plus 2955. Right, so this question is asking, why is this reaction not feasible at any temperature? Okay, so for a reaction to be feasible, Gibbs has to be negative. Okay, now in this case we have so feasible reaction, Gibbs must be negative. In this reaction we've got a positive enthalpy, and we've got a negative entropy, which means that minus T delta S is going to be positive. So because this is positive and this is positive, delta G will always be positive. Therefore, it's never feasible. Right, so let's have a read through this question. Although the reaction between CO2 and H2O to form glucose and oxygen appears not to be feasible, plants are able to make this reaction take place spontaneously by using photosynthesis. Beg your pardon. Each year, 3.4 times 10 to the 18 kilojoules of solar energy is taken in by all the plants on the Earth to make photosynthesis take place. Calculate the mass of carbon dioxide that is removed each year from the atmosphere by photosynthesis. Okay, right, so let's have a little look through. To be able to do this, you need the enthalpy change, which is on the previous page, 2879 kilojoules per mole. Okay, so looking through at the units, we have our energy and we have energy per mole. That means we can work out number of moles. This will give us the number of moles of CO2. But we're not asked for the number of moles. So you get 1 mark for getting this far. Either by showing it in this form or by giving the value here. So 1 mark for that. Final mark is you need to do the mass, which is going to be the number of moles times the molar mass of CO2, which is 44. And that gives us a value of 3.12 times 10 to the 17 grams. If you've got this value, even without any working, that's 2 marks. Okay, so 1 mark for this part, 1 mark for this part. So we've got a question on electrode potentials, redox systems on electrode potentials. Define the term standard electrode potential, including all standard conditions in your answer. Sometimes this is put as defining the meaning of standard. This one's a little bit clearer than other questions. So our definition. So this is our definition, along with the standard conditions. Oh, didn't mean to turn it blue, but hey ho. Write out standard hydrogen half cell in full, rather than SHE, abbreviating it. And 1 mark for each of these. You will get a mark with if you said 1 atmosphere instead of pressure, and you need the little degrees sign that I couldn't type. Okay, so for our next one, we're looking at a system based on redox systems 1 and 2. So we're looking at number 1 and 2. This is our magnesium is the more negative one, so that goes in the negative direction. And our copper is more positive, so it goes in the positive direction. Okay, so standard electrode potential. Is the more positive, or the right hand side minus the left hand side. The difference between the two, which should give you 2.71 volts. Okay. In fact, you didn't need to know the directions of the reactions at all for that. That's me not reading the question. Okay. The next part is asking you to write 3 equations based on equilibrium of 3, 4 and 5. So remember, whichever one is more negative goes in the backwards reaction, and whichever one's more positive goes in the forwards reaction. So if we are pairing 4 and 5 with aluminium, the aluminium is more negative, so in both cases aluminium will go in this direction, and iron and iodine will go in this direction. If we're comparing the iron and the iodine is more negative, so that will go in this direction, and that will go in the more positive direction. Okay, so I'm going to move this all up and write out the 3 equations that we get from that. Remembering that you need to multiply the equations. So in this case we've had to multiply the iron equation by 3 because it only gave out 1 electron, and you need to balance the equations before adding them together. Next one. So in order to get the same number of electrons in this reaction, we had to multiply the aluminium equation by 2 and the iodine equation by 3, giving us 6 electrons before we added it. And for the last one, okay, sorry for the bad handwriting, 1 mark for each equation. So why the reactions, even if the electrode potential says that it's possible, why might it not actually happen? And we've got 2 reasons. We could talk about high activation energy or slow rate, for 1 mark. And for the second mark, if you don't have conditions are not standard, or concentrations not 1 mole per decimeter cubed. Ooh. Problem with typing with these. Okay, it looks like you can only get 1 mark. So high activation, slow rate. You get 1 mark even if you've put both of those answers. So you need to be talking about this and non-standard conditions. And that should say or. It's rather difficult typing on my tablet, so I apologise. Right, almost to the end. Okay, so to help me out on this, I've copied over the equations from table 7.1. This is 6 and this one is 7. Okay, so this is a tricky one. You're going to have to spend your time thinking it through. We're going to start with the acid. So in an acid, which is kind of the situation that we've got in 7, that there's an acid present, equation 7 is greater than 6. So that gives us E cell is plus 0.27, so it's positive. So that means that equation 6 moves to the right. So, sorry, not to the right, to the left. And 7 moves right. Okay. Now, in an alkali, what we are doing is we are reacting OH minus with the H plus, so it removes RH plus. So that would mean that the electrode potential of 7 would be less positive. So remember, the bigger this value, the further the equilibria is in this direction. The smaller the value, the further it is in the left-hand direction. Therefore, E cell is negative. I've just noticed a typo. Sorry, it's just electrode potential. It's not E cell because it's only a half cell, not the whole cell. Okay. Right, so where do the marks come in on this? I'm running out of colours. Let's go for green. So 1 mark for saying that the electrode potential is positive normally. Assume this is acid even if you've not stated acid. and then you get 1 mark for saying both that 6 moves left and 7 moves right. Okay, next mark you say that the OH minus removes the hydrogen ions. So that means that this electrode potential is less positive. And I've actually missed off the final mark myself. It is a tricky question, this. For the final mark, I need to state in writing what I said out loud. So 7 would move left and 6 would move right. Okay, right. So for part E, we have to ask, what is the oxidizing agent? So remember, oxidizing agents, oxidation is loss of electrons. So therefore, an oxidizing agent gains electrons. It's going to be, sorry for the messy handwriting. Or are reduced. Okay, so the IO3 minus has gained electrons from SN2 plus. Would get you the mark, or you other ways of phrasing it, that the IO3 minus has been reduced to I2 or reduced to 0, or that this has oxidized, IO3 minus has oxidized tin. Sorry, the SN2 plus ions. Okay, the equation for this, you get 2 marks for getting all of this correct. If you haven't balanced your electrons properly, you can only get 1 mark. So to be able to do this, you write your 2 half equations. You know that this is going to this. Okay, so this is the easier one to balance. Just moved it up to give myself a bit more space. With the iodate, so step by step. First step is to balance the elements. We've got 2 iodines on this side, so we're going to need 2 iodates to balance that out. Next, we balance out the oxygens. There's 6 oxygens in total. And then, having added the waters to balance out the oxygens, we now need to add hydrogen ions to balance out the new water molecules. That's a total of 12 hydrogen ions. And the last step is to work out how many electrons we need to add to get it to balance. So our total charge on the left-hand side is -2 plus 12, which gives us 10 electrons. There's no charge on the other side. Neither of the molecules are charged. So then to get these two to join together, we need to end up with the same number of electrons. If we times all of the top equation by 5 and then combine it, we get our overall equation. Right, first one should be fairly straightforward. It's electron configuration of nickel as an element. So 3s2, 3p6, 3d8, 4s2. Doesn't matter if you've put the 4s2 first. In fact, that's probably more likely. But when we're emptying, we empty from the 4s first. So that gives us 3p6, 3d8. Having the 4s in here is completely correct. Chemists haven't decided which way they prefer having it, so don't worry about it. Okay, so next question, step 2, we added an excess of aqueous ammonia and then we heated it and we get this precipitate, and they've shown it to us here. If you look at the reaction on step 2, you'll see that ammonia has become the ammonium ion NH4+. That means it's gained a proton, so it's acting as a base. So NH3 gains H+ to form NH4+, so it is acting as a base. Right, coordination number. That's the number of coordinate bonds. So we have 1, 2, 3, 4 coordinate bonds, giving us a coordination number of 4. Asking us why it has no overall charge. So we know that it's nickel 2+, which means that as we have 2 DMGs, each one must have a -1 charge. So each DMG has -1 charge to cancel out the +2 charge on nickel. Okay, the next one's asking us to draw the structure of dimethyl glycoxamine. I have no idea how you pronounce this. So DMGH. Right, so we're going to have a look at our molecule up here. The dotted line is a hydrogen bond. So this is our molecule, but that's DMG, not DMGH. So we must have an extra hydrogen ion. Yes, an extra hydrogen ion attached to this, and the most obvious place is going to be here. That's the place that's going to easily be able to accept a hydrogen ion. So using that, let's see if I can move everything up. Give us a bit of space. That gives us this formula. Still struggling for space a little bit. For the DMGH, I'm sorry about the bad handwriting, but essentially it's a copy of the area I circled in green above. Okay, 1 mark. Okay, so our final one, we're looking at step 4. So I'm going to bring over the relevant information. We have 2.5 grams of the hydrated nickel salt. and 1.38 grams of the anhydrous nickel salt. From step 3, we know that the molar mass of nickel DMG2 is 288.7, and that we have grams per mole, and that we have a mass of 2.57. So that gives us this many moles of our original sample, so the first sample. Our original sample, we had 2.5 grams of it. We now know the number of moles, which gives us a molar mass of 280.9 grams per mole for our hydrated salt. Now, the second sample was also 2.5 grams, so it's going to have the same number of moles. The anhydrous salt is going to have a molar mass of 1.38 divided by the number of moles, giving us 155.0 grams per mole. That's the anhydrous. Okay. Right, so let's move this up slightly. There's more than one way around this, but to work out the molar mass of our water, it's going to be the difference between the two. So that's going to be the molar mass of our n number of water molecules, which comes out at 25.9. If we divide that by molar mass of water, that gives us 7. So therefore we have 7 waters of crystallization. Okay, right, so we've got a number of waters of crystallization. We still haven't worked out what our anion is. So we're in this situation where we have N and then a negative ion that I'm going to call X and 7 water molecules. But we can now work out the mass of X, or the molar mass of X, by taking the mass of our anhydrous ion, the molar mass of our anhydrous ion, and taking away the mass of the nickel. Tells us that our anion is 96.3 grams per mole. And it's got a 2- charge. If you guys think through common ions that you know, hopefully somewhere in there sulfate ion should occur to you. If you check its molar mass, that comes up at 96.3, giving you an overall formula of nickel sulfate and 7 water molecules. All done, total of 13 marks.